hopefully this works for the rest of the class. I know what you're talking about on problem. Never seen you wear a hat. It really threw me off. Okay. What's that?
Did you take the first exam off my stats lab?
Don't think so.
Because it doesn't show up on mine at all.
I don't know. Maybe I did on accident. You're saying it's not there?
So then for number 10, can I get full credit on that one?
Yeah, number 10 was goofy.
Because technically I got the right answer.
Technically, you got a T interval,
Yeah.
and there's no reason you would have assumed you should have done a Z interval.
Why do
Yeah, I agree with you, actually.
Why do we assume that when the formula is the T value?
You should have just assumed it was T because I forgot that this book doesn't do Z intervals, or doesn't really talk about Z intervals in detail, and we skipped them basically.
Yeah.
So for means they don't talk about Z intervals. This is our first quarter on this book. But yeah, I agree with you on number 10. There's no reason you would have thought to do a Z interval because we never talked about doing Z intervals for means.
Right.
So I agree with you. Yeah, that one should have been marked correct for anybody who provided the T interval response, which was because if you looked up the T value is like 2.003 or something on that problem, and a lot of people use that, and I was using the Z value because it said assume this population standard deviation, but we kind of never went through that scenario in class, and so that's what.
So do I just mark 10 full credit?
Yeah. Just on 10, you can just say, "Hey, I was right."
You were wrong. I was right.
Yeah, because that happened to more than just you. Were not the only one affected by that problem. Yeah. My online students, they get on me a little quicker than you guys, so they already got on me about that last week.
Well, they're online.
Right.
I was just going to save my harassment for Monday.
Yeah. So, yeah, that's right. Okay. Other questions? Yes.
Number 18.
On the...
It's the one about
Yeah, that one was also misleading at the end because it was a similar problem to the one I gave you. It was almost the exact same problem as the one I gave you on the practice final, but I changed it because I wanted to turn it into a one-tail test. So, right. So if you look at the description makes it sound like a two-tailed test, but I forgot to delete the last section, little sentence that said two-tailed p-value or whatever.
That's what got me.
Yeah.
The right answer, but then when I saw the two-tail, I changed that.
Yeah. So I meant to take that out and treat it like a two-tailed test or a one-tailed, but then with the two-tailed in there, it confused a lot of people, which makes sense because it was confusing, and then so that one should have been. Yeah, I should have took that out and I didn't. Yeah, that was fine. Yeah, that was fine. So if you gave me the two-tailed p-value, well, I won't take all four answers. I'll take either the one-tailed or the two-tailed p-value for that one. So if you got the one-tailed or the two-tailed p-value in your original test, I'll take it.
For what answer?
That was 18. So a lot of people gave me the two-tailed p-value, which would have been doubled the one-tailed p-value.
Yeah, that's what I did.
Yeah, and so I'll give you that one back if you gave me the two-tailed p-value. If you gave me one of the other two, then you can just redo it for half credit. But if you gave me one of the original correct answers, I'll give you full credit on that one. Yeah, I also heard about that one over the weekend from a couple of people. What's that? I don't. Yeah, I'm not disclosing. No, I think that was it. I'm pretty sure. I don't think there was a problem with those ones per se. I don't think there's a problem with those ones. So, okay. Let's see. So everything should be okay. The homework's extended out. I'll post the take-home exam. I was working on it yesterday, but it got a little bit out of hand. And I got myself up to like 55 problems, and I was like, this is a problem, so now I'm going to have to scale it back a little bit. So I'm going to do that this afternoon, and I'll put it out for you tonight. Yeah. For the take-home portion, though, and you got a week to do it. But I'm going to scale it back a little bit.
Like 30?
Yeah, it got a little crazy. I was like, dang, this is going to be good. And then I was like, 55 is not going to be good. So I'll have that out no later than this evening though. So that'll give you a full week to work on it because our final is next Tuesday. So you'll still have that full week. I decided I probably will put a practice test out as well for the final, for the in-class portion. But that probably won't come out until tomorrow. I won't get around to that until tomorrow probably.
Hey, what
Yes.
time's our final?
That's a great question. I do not know. That sounds right to me.
Don't listen to me. No one's.
No, that sounds right. Isn't it? Is it 11:30?
Yeah, they said that they finally got them arranged so your final starts at the same time as your class.
No.
No?
No. That cannot be true.
That's what the Spanish teacher said.
I don't think that's possible. Don't ever assume that's true. You should always check the final schedule. Because they don't necessarily always start at the same time. They'll always start within like an hour of your usual class time, but sometimes they start before or after your actual class time. Yeah. But yeah, I think ours does happen to be 11:30 this time.
Yeah, that's what I thought.
Yeah.
I guess what you said last week, but I wasn't sure.
Mm-hmm.
In this class?
Yes. This is the goofiest computer. And then it comes back at weird. Okay, anyways. All right. So, we're going to finish. How big is this thing getting? Is it getting pretty big? Yes, it's getting pretty big. I'm just going to start a new one. And then I'll just... All right. You ready? We're going to finish this off. So this is just going to be... This is really just the last section. I want to say that's 10.3. Okay? So this is the end. Okay? But I just split it into the second part because my other one was getting way too big. So, in the last section, we were talking about hypothesis tests. So, we were doing them for proportions. Right? So, if you want to do a hypothesis test about a proportion, right, you had the null hypothesis was that it was equal to something. You had some alternative hypothesis, maybe greater than or not equal to or something like that, right? So we came up with two approaches, but they both hinged on the same test statistic. So the test statistic we were using was a z-value, which would be your sample proportion minus the null hypothesis. The standard deviation downstairs we used as this, something like that. Yeah? All right. And then from there, we could either go compare it to a critical value, or we could take it and we could get a p-value off of the z-table. Yeah? Sound vaguely familiar? Right? Your critical value and your p-value are based on your alternative. So if your alternative is not equal to, you could go, you'd have to split your alpha in half. If it's a one-sided, you load up all your alpha on one side of the tail. But actually, when we did have that, there was also that other option, though, that we kind of talked about, but a lot of people didn't really think it was very cool. I thought it was pretty cool. But if your alternative was a not equal to, you could just do a confidence interval as your test, right? So, anyways, that's great. Proportions, fun, and everything. But we've also spent a lot of time this quarter talking about means. So the last thing we want to talk about is hypothesis testing about averages. All right, so that's what we're going to cover this time. So hypothesis tests about mu. Luckily, just like the confidence interval examples, we don't really have to do a whole lot of extra work. We pretty much have the whole the whole strategy and setup all together. So the hypothesis tests are still going to look exactly the same. So there's going to be some claim about the average. There's going to be some alternative. Not equal to, could be greater than, could be less than, one of those, right? It's going to be one of those three options. And we're still going to basically take the same approach. The problem is, so we could actually take an exactly identical approach if we could calculate a test statistic. We could calculate a z-value because we know that if you take the sample mean minus the true mean over the sample standard deviation, you get a z-statistic. But what was the whole reason that we didn't use a z-interval for our confidence intervals about means? Why didn't we use the z-interval? Because what do we not know? What's probably unknown here in that z value there? The sample mean is definitely known. Sample size is known. The mu naught is the claim, but the one thing we don't know is necessarily what. Yeah, so typically the true standard deviation is unknown. Right? Because that's a population standard deviation. If you know your population standard deviation, then I would think you probably have enough data or information about the population to know a lot about the mean too. So what did we do in the z-intervals? Instead we did what? Instead of z-intervals we made t-intervals. So we can do the same thing for hypothesis tests. So we say, okay, so this strategy isn't going to work if we don't know the population. So what we do instead is we calculate a similar test statistic using the sample standard deviation, right? But we're going to call that a t-statistic rather than a z-statistic because it's going to have a t distribution, not a z distribution. And we're going to use this. It's just that now our critical values and our p-values, they're going to come from the t-table. I ran out of room. T-table, that's what it's supposed to say over there. My computer didn't let me write over there. Anyways, okay? So it's going to be the exact same approach, but now everything is we're just going to use the t-table instead of the z. Just like with confidence intervals, rather than using the z-value, I had to go get a t-value. But we'll still get our critical values the exact same way. It's going to be based on our alternative hypothesis, right? So if your alternative, is mu less than mu naught, you're just going to go to the t distribution, load up all your alpha level down there, and get a t statistic, right? If your alternative is mu greater than mu naught, you're just going to load up all alpha level up here and get a cutoff, but we're going to be getting t alphas instead of z alphas, right? And then if your alternative is not equal to, just like before, we're going to split that alpha level in half, right? Alpha over 2, and then our cutoffs will be, t alpha over 2. All right? You just have to remember, in the t distribution, we're going to have this degrees of freedom that we're also going to be taking to the table along with us. All right, so we'll be taking an alpha level and degrees of freedom to the table. That's really the only difference, though. But it doesn't change the overall process. Now, getting a p-value is going to be trickier. So we're not going to be able to get exact p-values. We're only going to be able to approximate them, but I'll show you how to do that in a little bit. All right. Now remember again, too, just like before, you could also just use a confidence interval if you'd rather on the two-tailed alternative. Okay. So that's also an option here. Just make sure you're doing a t interval. All right. So, let's do an example. Yeah? Yeah? Let's do it. Okay. All right. So, let's say that a realtor, let's say that you're looking for, you're looking at maybe buying a house in a particular neighborhood. So, a realtor tells you that the average age of houses in a particular neighborhood is 24 years old. Okay. And but based on kind of driving around the neighborhood, you think it may be older. Okay. So let's say you decide that you're going to test this. So you're just going to randomly select some houses on. You're going to randomly select some houses in the neighborhood. You're going to look up their build date, like when they were first sold, and then you're going to use that to calculate an average. So let's say that you go out and you sample, let's say 18 homes in the area. And from those 18 homes, you get a sample mean of 26.3 years old. And a sample standard deviation of 4.3 years. Okay. Now, was your sample average more than 24 years old? Yeah. Does that mean that the true average of all the houses is more than 24 years old, though? Not necessarily, because we only sampled 18 houses, right? And there's some variability, obviously, in the houses you sampled. So some of them are younger and some of them are newer. So we want to make sure that we're not just going to discount the claim based on, this mean alone. We want to do a hypothesis test. So let's go ahead and perform our test at, say, the 0.05 level. Okay. All right, so what is the formal hypothesis here? So remember, your null is always equal to, we're talking about means, so we're going to use mu's, right, not p's. Okay. What would be our null and what should be our alternative here? Okay, so the claim is 24. We believe what may be true? Yeah. There you go. Right? So the claim is 24 years old. We think the truth might be greater than that. So now we're going to go do a test. So I'm going to do it just like we did before. First, I'll take a critical value approach. All right? So let's say we want to do the critical value. So if we're trying to get a critical value, all right, our alternative is that mu is less than got that backwards, didn't I? Our alternative is greater than. Yeah? So then our cutoff is going to be up here, and we're going to put all of our alpha level, right, up here, and we're going to go get a t, so 0.05. Now, what are our degrees of freedom here? Our degrees of freedom? Yeah, so 18 minus 1 is 17. Okay, so that's our degrees of freedom. So we need to go to our t table and find t sub 0.05 with 17 degrees of freedom. All right. Let me go get my book up here. You guys probably all have t tables, hopefully, still. I don't have my paper copies of them. I remember I gave some out a while ago. But we can get one up here, too. Okay, it's somewhere back here in the appendix. T-table. Here we go. All right, so we're looking at t sub 0.05, so we're in the, fifth column? Going down to 17 degrees of freedom. What is it, 1.5 1.74 is what I see. Yeah? Everybody seeing that? All right. So that'll be our cutoff. Okay. So then our cutoff's 1.74. So where's our rejection region? Above or below? Yep. So our rejection region is up here. And so if our t-statistic gets any bigger than 1.74, we're going to reject. So now what do we need to actually go do? Not yet. We need one. Yeah, we haven't actually gotten our t-statistic, right? So we got our critical value. So now we need to go actually get our test statistic. So our test statistic here, because we're dealing with means, is going to be a t-value. So we're going to take our sample mean minus the claim divided by the approximation of the standard deviation. So then that's going to be, our particular mean was what, 20-something? 26.3. The claim was 24. That's your numerator. Downstairs, our sample standard deviation was what, 4-something? 4.3. And we sampled 18 homes to get those results. So what t-statistic does that give you? Is it 2.274?
That's
2.269? 2.269? Other people get that? Okay. So the t-statistic is a 2.269. And is that in our rejection region? Big time, yeah. That's pretty far out there. So it's way out there in our rejection region. So if that statistics it exceeds the critical value, it's in the rejection region. So what should we probably do? Yeah, we should probably reject the null hypothesis. So does it look like homes are or are not older than 24 years old? Yeah. Dude, this is 4 more days. So yeah, the idea was our null was 24. Our alternative is greater than. So since we're rejecting our null, that means we're saying there is evidence for the alternative. So it looks like, as far as we can tell, homes are older than 24 years old. On average. All right. Okay. Any questions on that one? You feel pretty comfortable with that? It's really pretty much, like I said, it's almost exactly what we were already doing. We're just going to use our t-table instead of z-table. What questions? No? Yes, we can. But I want to show you how to get a p-value here first, okay? Because the p-value is really tricky. Because remember that for a z-table, we had probabilities associated with every z-value from like -4 all the way up to +4. It doesn't work like that on the t-table. Okay, so in the p-value approach, what do? You don't go get a critical value. The very first thing you do is you go do what? Yeah. So in the p-value approach, you go straight to the test statistic, which in this case, we already calculated, right? Which was 2.269. Yeah? Now, if we were going to traditionally go get a p-value for that, this is a one-sided test, so we would take 2.269 to the table, and we would look up the area above, and whatever this is, that would be our p-value, right? Take it to the table, get the area above or below, or however you have to do it depending on the alternative. Okay. But remember that this is a t-distribution with 17 degrees of freedom. It's not a z-distribution. So we can't use a z-table to get a p-value. We need to use the t-table. But what happens if you go look at your t-table with 17 degrees of freedom, is there anywhere where, is there a t-value of 2.269 anywhere on that row with 17 degrees of freedom? There's not, right? What's the closest you can get to 2.269? With 17 degrees of freedom? Here's 2.11, 2.224. That's pretty close, but it's too small. But then if you go over the next column, it's 2.567, right? Okay, so could we approximate the p-value even though we can't get it exactly, though? Mm-hmm. What is our p-value? Give me a range. Where does our p-value have to be between? Yeah. So since our test statistic is between here and here, that means my p-value is between here and here. I'll show you. I'll draw a picture to show you why. Because it says, okay, with 17 degrees of freedom, by the time your t-statistics hits 2.224, so by the time it hits 2.224, then this area right here is 0.02. And then if you jump up to whatever the next one was on our chart, it was 2.567. So 2.567. I'll make this bigger in a second. Then this area right here was 0.01. Okay. Well, where was our test statistic? Our test statistic is right here, right? Our test statistic is 2.269, which is beyond that one, but not beyond that one, right? So it means that our area, it's going to have to be less than 2% because our test statistic is beyond this one. Yeah? So it's got to be less than 2% because this is our actual p-value we want. But it's going to be more than 1% because it hasn't reached the threshold of 1%. So what we can do then, so since our t-value is between 2.224 and 2.567, I don't really need an equals to there, then that means that our p-value is going to be between 1% and 2%. But is that still a low enough p-value for us to reject, according to our setup? Because what alpha level were we going to be testing at? Mm-hmm. So then if our p-value is less than 0.02, then it's definitely less than 0.05, right? Which was our alpha level. So we would still come to the same conclusion to reject our null hypothesis. Okay. It's a little less straightforward than it's Z. But as long as you have a bound on it, you should be okay. Because we only have to compare it to alpha. So as long as we know what it's bounded between, then we can know.
So we could just do either or, we don't have to do that there.
Unless your homework specifically asks you for a bound on the p-values. Right? Mm-hmm. Yeah, and the thing is that it seems like the p-value approach is more complicated, I think. But the reason the p-value is nice is it tells you how strong the evidence is. So like typically in research, if you're reading like a research paper, what they'll do is they'll say, there is evidence, that the drug is effective or whatever. And then what they'll do is they'll report the p-value that they attained when they did the hypothesis test. And so what it's doing is it's telling you how strong was the evidence in favor of their alternative. So like here, this is a really small p-value, so it's pretty strong evidence, right? And typically what we do is, it's like if your p-value is greater than 10%, that's pretty much no evidence, right? But what happens is that then if your p-value, if it's between, say, like 5% and 10%, then now you're starting to see some evidence of the alternative because your p-value is getting lower. You would reject this at the alpha 10% level. When you start to see p-values between, say, 1% and 5%, that's pretty good evidence. We would say maybe strong evidence. And then when you start to see p-values that go below 1%, that's we would say that's very strong evidence. So it seems complicated, but it's more, the p-value is actually more informative than just making the decision. Because I could tell you, let's say you're testing the effectiveness of a drug, right? There's a big difference between a significance level of 0.0 or 0.004, or if I told you that the p-value is 0.049, right? That's a big difference, because if my p-value is only 0.049, that's close to 5%, and that's pushing the limits on our typical alpha level. But if my p-value is 0.004, that's really, really strong evidence. Okay? Does that kind of make sense? Remember, low p-values are when you reject. So, typically, this is how you're going to see it reported. They're going to tell you what they decided, and they're going to tell you the p-value that they obtained to make that decision. So it is useful. The p-value is useful. That helps you quickly decide.
So that's what I was talking about. The agrees with the p-value is greater than or equal to the alpha. You do not reject.
That's right.
The p-value is less than the alpha, so reject.
Yeah, because when we're talking about evidence, we're talking about evidence for the alternative, not the null hypothesis. So as p gets really small, then we're leaning a lot more towards our alternative than the null. So if the p-value is low, then you reject the null hypothesis. Okay. Yeah? All right. So low p-values are good typically if you're trying to prove something, is the moral of the story. And the one thing you do have to be careful about, though, I'm going to do another example, but the other thing you have to be careful about is what we call statistical significance. Versus practical significance. Okay. So statistical significance, all statistical significance means is that the p-value was low enough to reject the null hypothesis. That's what we say when something is statistically significant. It's like we did the test, the p-value is really low, so there is evidence to reject it, right? But practical significance is, does it actually matter? And the reason that they can change sometimes is that if you have a big enough sample size, you'll always be able to find statistical significance in your results. Okay. So a big enough N will always produce statistical significance. Even if practical significance isn't there. So like, as an example, let's say you were looking at, say, like a blood pressure medicine. Okay. And maybe the current meds, they maybe lower your blood pressure by, maybe whatever, 30 points or something. I don't know how they measure. I don't know if they call it points or whatever. I don't know how they measure your pressure, but so the current meds, the average is that you take the meds, they'll lower your systolic blood pressure by 20 points or something, or 30 points, right? And maybe you come in and your new med, maybe in reality, it lowers blood pressure by, say, 30.1 points on average. Is that really a practical difference? Not really. But if you had enough samples, you could show statistical significance and say, yeah, this new medicine is actually better. It lowers things by like a tenth of a point more than the old stuff, right? So if you had a big enough sample size, you'd see that. But is it actually practically significant? Not really. Okay. So if you see really big sample sizes, then they don't really mean that much, because it could be actually a really insignificant difference. All right. Anyways, this is also the really super annoying thing about, so I'm kind of biased, but anybody in here going to be a psychologist or sociologist or anything like that?
I wanted to.
That's okay. Anyways, I'm really biased. Psychology and sociology, like the what do they call them? They're not the liberal arts. They're the social sciences. So research in social sciences, they like to use this thing called the odds ratio. This is not, you don't have to write this down, but this is really annoying to me. So if you see this, you need to be really skeptical. Okay? They talk about this thing called the odds ratio, and they'll say things like they'll say that such and such, some drug increases the likelihood of, I don't know, heart attack or something, or whatever, and then it'll give the odds ratio like by 2 times, like 2.5 times, right? And they're saying that what it did is they're saying that people who took it were 2.5 times more likely. But if you look at like the raw rates, right, then it might be they might be looking at a raw heart attack ratio of like 0.001 to 0.025, right? And so they're talking about statistically this might be a significant difference because it did raise their risk by 2.5 times. But look at the incident rate of the actual heart attacks, one med versus the other. Is that really that big of a difference in incidence of heart attack rates? And the other thing, too, is it's really annoying, is that if you look at the confidence intervals on the odd ratios, then the confidence intervals on the odd ratios will go from something like 1.03 to like 3.56 times. So it's saying that the odds ratio could be as low as 1.3 times more likely. So even though like this is like an average odds ratio, it's 2.5 times, the true odds ratio could be as low as like 1.03 times, which means like almost no significance at all. So just be really careful. That might not have made any sense. But the point is that they're trying to make the results look really important so that they can publish a paper, because there's a lot of pressure in academia to publish papers. So they try to make it look really, really impressive by reporting odds ratios. But when you really look down to it, not only is the odds ratio not super significant, but then if you look at their confidence intervals on their odds ratios, they're down to the point where it could be almost negligible. So anyways, just be skeptical when you see odds ratios, okay? And if you're going to be a psychologist or sociologist, I hope I did not offend you. But they should have just hired a statistician. That's the answer. But anyways, okay. let's do another. We got time for another example for these t intervals. All right. So there was an example they had where they were looking at the effects of alcohol on adolescents. Obviously, this is not something you can really do an experiment on because you're not allowed to take a bunch of adolescents and give them alcohol. But you could do some observational studies, okay? And what they specifically looked at was they looked at the volume of their hippocampus. Anybody taking psychology right now? It's okay. What does your hippocampus do? Yeah? Yeah, well, and one of the things that the hippocampus controls is your decision-making skills, right? So what they were looking at is they're thinking like, if adolescents use alcohol, does it decrease the volume of their hippocampus, which could potentially be a sign of decreased decision-making skills, even when they're not drinking. Okay, so they want to look at how alcohol affects the hippocampus.
It doesn't.
Does the hippocampus? It doesn't. Does the hippocampus control like your adrenal glands, or is that something else?
Something else.
Okay, I don't remember. It's been a long time since I took psychology, but I know it controls decision making. All right, so the normal volume of an adolescent hippocampus is 9.03 cubic centimeters. So obviously we can't take a bunch of teenagers and start giving them alcohol and then measure their hippocampus. There's some ethical issues, but what they could do is they can look at adolescents who are participating in like therapy programs for alcohol abuse. So maybe they've gotten in trouble with the law or they've been self-admitted to an alcohol recovery program. So this is what they do. Okay. So what they did is they randomly picked 12 adolescents that were participating in some sort of alcohol therapy program. Okay, so they're self-reported or known to have abused alcohol. And what they found from those 12 is they calculated an average hippocampus volume of 8.10 cubic centimeters, and a standard deviation among their hippocampus volumes of 0.7 cubic centimeters. All right? So what we would like to do is we would like to test at, say, the 0.01 level if alcohol affects hippocampus size. So in our sample, were our adolescents' hippocampus is smaller than average? A little bit, right? The question is that actually significant or not? Okay, so what do we need to do to solve this? We could do a critical value approach first, right? So the first thing we need to do is what would be a null and alternative hypothesis? So up front, before they got these results, they just wanted to know if alcohol affects the hippocampus volume. So without seeing any prior results, what would probably be the most appropriate alternative? Less than, greater than, or not equal to? Yeah, I mean, I've kind of given you a hint because I've showed you the results. But typically going into research, you might pick a not equal to if you don't know for sure if it's going to go up or down. Because it's possible you might think that maybe it affects it, but maybe it enlarges your hippocampus, or maybe it shrinks your hippocampus. We could test it either way, but I'm going to run it as a not equal to alternative. So the null assumption before going into this experiment, we should just assume that these adolescents' hippocampuses are going to be what? Yeah, normal, 9.03. And then we're going to see if we can prove otherwise, something other than 9.03. So this would be your assumption going in. Because remember, when you're going in the experiment, you don't have the luxury of seeing the results on the other end of it. Okay. So this will be our null and alternative hypothesis. So then now we're going to use that to go get some critical values off our table. So since this is a two-sided test, what do we need to do with our alpha level? Yep. So if our alpha level, so remember we have a not equal to alternative. Our alpha is 0.01. So we need to take that 0.01, put half of it in the bottom tail, half of it in the top tail. And so our cutoffs are going to be t sub 0.005 and negative t sub 0.005 with how many degrees of freedom? Yeah, because we had 12. We had 12 students, so 11 degrees of freedom. So if you go to your t table, look up t.005 with 11 degrees of freedom, and what do you get? 3.106. Which would mean this bottom one would be a negative 3.106. Okay. All right, so you can look that up on the table later to confirm that, but I see enough people agreeing that I think that's probably true. All right, so now we have our cutoffs, which means our rejection region is everything outside that. So now what do we need to go do? Yeah, so then we'll go get our actual test statistic. Our test statistic is that t-value. It's the sample mean minus the claim over the sample standard deviation divided by the square root of sample size. So our sample mean was 8 point something? 8.10. The null hypothesis was 9.03. Our standard deviation was 0.7. And we looked at 12 samples. So that was our... What do you guys get for a test statistic here? 602. Pretty big. Pretty big. That's pretty big, so what do you think we should do here? So here's our cutoff. Where is negative 4? Way out here. Yeah, I think we need to reject this. I mean, that's a huge test statistic. When your test statistics start getting above 3 or 4, I mean, you're definitely going to reject. That's pretty significant. That means your results were pretty far from the claim. So this is in the rejection region. So then we should reject the null hypothesis. So what are we actually saying? If you go back to the actual test we began with, what's happening here? Or what does it appear is happening? Yeah, it looks like alcohol does affect hippocampus size in adolescents. Yeah? Because the null hypothesis was the same as everyone else. The null hypothesis was no effect, so the alternative is that it has an effect. In this case, it looks like it shrinks it. Looks like it somehow shrinks their hippocampus volume. Who knows? It might do the same thing to adults, but at least in adolescents, we see some significance. All right. Questions on this example? I'm going to get you the p-value in a second, but questions until we go there. Before we go there, about this, what questions do you have on this example? Does everybody know how to get the critical values? Okay, and everybody understands why we split our alpha level in half? Okay, cool. Two-tailed test, yep. To get the p-value, so for a two-sided test, remember, we have to double our p-value. So what we have to do is we have to think, okay, ours was down here, negative 4 point, what was it? 69 or something? 609? whatever. There's no 9 there. Whatever. It's negative 4.6 something. Okay, and so but on a two-sided test, we need to get that side, but we need to double it. So our p-value is actually whatever's below negative 4.62 and above 4.602. But if you go to our table, our degrees of freedom was 11, right? So if I try to take that to my table with 11 degrees of freedom, right? What happens down here? How my table only goes to 4.437, right? Yeah. So since my test statistic is beyond that, what's going to be true about my p-value? How's it going to compare to this number? It's going to be lower than that, right? So my p-value in that tail, since my test statistic goes beyond this, it's going to be less than 0.0005. Okay. So this right here, this is going to be less than 0.0005, and so is this. So overall, what can I say for sure about my p-value? It's going to be less than the sum of those sides, right? This side has to be less than 0.0005. This side has to be less than 0.005. So overall, my p-value is going to be less than 0.001 if you add those up. Is that a pretty small p-value?
Yes.
That's a very small p-value. It's still very significant. So that's way less than our alpha level. I don't even know if we didn't establish alpha level, right? It was 1%. So that means our p-value is less than 0.001, which is less than 0.01, which was our alpha level. And if our p-value is low, we have to reject the null hypothesis, which is what we already did in the critical value approach. But now we have a bound on our p-value. And so if you report that, say p-value less than 0.001, that tells me that this was an extremely significant result. All right? Any questions on that? Cool. Could we have done it another way? We're out of time, but could we? It was not equal to alternative, so we probably could have just constructed a what? Yeah, we could have just constructed a confidence interval. But I'll do that one. I'll do that one tomorrow. I'll finish it off with the confidence interval tomorrow. I'll take your test corrections.